Hello and welcome back to another episode of the Oxford MAT Livestream. Today, Trigonometry. Good to have you with us. If you're joining in live, you can join in with Slido chat, which is up there on screen at the moment. Moderating Slido chat today, we've got Georgina, who's a DPhil student at Oxford. That means that means postgraduate student. So Georgina's got a maths degree and is doing a PhD with us. You might have met Georgina before if you watched the Oxford Online Maths Club, which was, there we go, let's get chat just like that. Oxford Online Maths Club. Georgina was on showing us about finding roots of polynomials with small parameters and things moving around. So maybe you've met Georgina before. She is very keen to answer your questions. I will do my best to keep an eye on chat as well, but there we go. Good to have you with us. Hello everyone. If you're joining in Slido, I would like to know, how is your day going today? You can vote on a scale from 1 to 5. Those are the options. Someone says they're watching the MAT live stream to procrastinate from doing past papers. Just you wait, because we've got this episode and then we've got another one next week. And then we've covered the MAT syllabus, so MAT live streams are going to be a bit more focused on past papers after that. But at the moment, we've still got a bit more syllabus to cover, haven't we? Because we've got trigonometry this week, and we've got sequences and series next week. Sequences and series I'm looking forward to. It's sometimes the case that people haven't learned that material yet at the time that we go live with the MAT live stream. Maybe you're going to learn it in September when you get back after the summer holidays. But maybe we'll learn it together next week. But hopefully trigonometry is something that people have seen before, maybe a little bit at GCSE or equivalent, which then develops a little bit at A-level or equivalent. We will see. Hello, can we see who have we got in chat? So we can see anonymous people, so as a good reminder, you can be anonymous in Slido chat. And hello to Hector and Riley and Cookie and Kay and Hugo and somebody set their username as Mames Junro, which, yeah, well, there we go. Sensational, it's pretty good. Yeah, you can put your username down as your name if you like, or not your name. There we go. Hello to Jacob, Evie, and Ginger Biscuit. There's a mild biscuits related sub theme going on, which I'm not going to claim to understand. Right, I noticed that somebody, I wanted to know I noticed down this end. Somebody's having a terrible day, but they've tuned in live to see some maths anyway. So the only thing I can say is I hope that the maths improves your day. But it looks like most people, maybe with the onset of the summer holidays, are having an even better day than normal. So that's good to see. I think 4.3 is one of our highest averages. So there you go. Ooh, yeah, there you go. A couple more people voted 5 while I was pointing at it. There you go. I found the key to engagement. Point at the thing that you want people to engage with. There you go. Good evening to Annoying Integrals and Neat and another anonymous. Am I looking forward to another year of admissions, says anonymous person in chat. Well, you know, they keep coming. They keep coming around. I haven't quite finished the previous one because, of course, we've got A-level results day in a couple of weeks. That's one of the reasons we're taking a bit of a break from MAT live streaming. A-level results day for me, but hopefully that's no work at all. Hopefully all our offer holders just sail through and everything's fine. Right, good. Just here for fun. Should we be doing Pat? Well, you could do Pat, but Pat has got maths questions on as well, possibly involving triangles. Who knows? Maybe. I don't really have anything to do with the physics admissions test, but I'm sure they wouldn't mind if you were good at triangles. I can't think of any physics immediately that needs loads of triangles, but I don't know. You could shoot a laser at some sort of angle, in a safe environment, of course. Right, but let's leave the lasers to the physicists, and let's look at what's going on with the trigonometry. Sitting ESAT, yeah, people doing all sorts of tests, but still want to do some maths. And somebody asked how my day is, which is nice of them. I think I'm having a 4-star day. I tidied the office. You can only see a tiny part of the office in the background, but I've tidied the office, and it's only me in today. So I take the opportunity to tidy things. We will see how the team feels about this when they get back. Who writes the math? Big team of people. Lots of people write math questions. It's part of my job to make sure it happens, but that doesn't mean that I write all the questions. Right, okay, chat is going to vanish from your screen. I can still see it, and Georgina can still see it. So there we go. Hector asks, just as having just moved it over there, Hector's asked how different it's going to be because it's on screen. Well, it's going to be the same as last year, and since a lot of it is multiple choice, not that different from the multiple choice questions that we've set before. The long questions, people are going to type their answers, but spiritually, it's being set by the same sort of people. It's being set for the same sort of reasons, and it's being done by the same sort of people. So spiritually, not very much has changed since 2023, 2022, depending how far back you look. Right, okay, here's the syllabus. We are supposed to know how to solve simple trigonometric equations. We're supposed to know some identities along the top there, and we're supposed to know that sine, cosine, and tangent are periodic functions. Different period for tan, because that's got a period 180 degrees. And we're supposed to know the sine and cosine rules for triangles. If you don't know what those are, I've got them in the revision notes just under here. And quick reminder for people, look, revision, that's what triangles look like. If you would like a copy of these notes, there's a link in the YouTube description to that worksheet up there. And you can get all of the worksheets for the MAT Livestream on the MAT Livestream homepage, which is this link just next to me, which is also in the YouTube description. And I hope that if you type MAT Livestream into some sort of search engine that you get here. Right. Okay, what common errors do candidates often make on the maths? Well, they just get the questions wrong, but that's all right. What's my advice for avoiding it? It says, so sensational. My advice for avoiding it is just get better at solving the questions. Sorry, it's really hard, isn't it? Yeah, good, okay. Are there different questions for CS? No. Right, okay. Having said I would switch off chat and not get distracted by it, I seem to be getting more and more distracted by it. What should we do? Let's have a look at the revision notes together. Is that going to load? That is going to load, there we go. Test registration is open, of course. You know this because I put that up at the start of every week. You've probably already registered, right? Yeah. All you need to do is start a UCAS application so that you get a UCAS ID, and then you could register for the MAT. It's online registration. You could do it any time of the day or night, I think. So maybe you could do it at the same time as watching this. Who knows? Right. Yes, Hector is not correct. I'm afraid there used to be CS only questions, but this year there are not. Please read the instructions on the MAT page carefully. We changed the format in 2024. Yeah, questions are now same for everyone. There we go. Okay, good. Registering for the test does not commit you to taking the test or applying for Oxford or anything. It's a necessary condition if you would like to take the test. It's not actually sufficient. You also need to make an application, and yeah, you're allowed to do other. You're allowed to change your mind. There is no long CS question on the maths anymore. There used to be. Right, is this a surprise for people? I'm not sure. The questions are there's a format for maths. Let's do this. We'll learn about triangles in a second. Format for math this year: 25 multiple choice questions, 2 longer questions. Same for everyone. Maths and philosophy, computer science and philosophy. The other one, maths, computer science. Everyone's doing the same 27 questions on the MAT. If you look at past papers, they've got, well, some way of counting 7 questions. But one of those contained lots of multiple choice questions within it. So not much has changed really. If you register and don't take it, will that affect other questions? Nope. Just need you to sign up to take the test if you're going to take it. It doesn't affect anything. We don't. I mean, people always seem to think that these things are a bit of a trap or something. Anyway, August 18. How quickly do you need to book? That's a good question. Right, hang on. Chat's going off. I'm putting chat back on. Chat's coming back. How quickly do you need to book to get a preferred test centre? I don't know. I'm encouraging people to do it as soon as possible. Last year, it wasn't like it's not like booking festival tickets as far as I remember from last year. It's not gone immediately. In my experience, lots of people left it later on. I'm encouraging people to book earlier so that they get it done. Right, okay. Yeah, good. We will not look at TMUA scores. We will not get TMUA scores. The Oxford uses the maths admissions test. We do not use the test of mathematics for university admissions, which is a different test. you could get no points in TMUA and we wouldn't even know. But I hope you do well in it. Okay, right, good. To be honest, we would have to tell you, right? If we were going to use TMUA scores, we're not allowed to secretly use TMUA scores. We would have to tell you. We couldn't just quietly ask the Cambridge people what you scored in the TMUA thing. We would have to tell you. When you sign up to take it, you would have to tick a box to let us. Yeah. All sorts of things. And a couple of questions coming in about how the multiple choice questions this year are going to be labelled either 2 marks, 3 marks, or 4 marks. And the question is, does that have anything to do with the difficulty? Well, I mean, different people find different things, different difficulties, but we have decided which ones are 2 marks, which ones are worth 3 marks, which ones are worth 4 marks. So, good, okay. Pythagoras can be used to derive a trig identity. Can you use other things to derive trig identities? I'm going to say any extra identities you invent are probably not on this list, and I really do want to look at the list now. Right, okay. Jack can keep going. Georgina, if you're watching, good luck answering the questions about the format of the MAT this year. It's the same as last year, but... okay, right. We've got revision notes about what sine and cos and tan are. I hope they're not a surprise. They're to do with right-angled triangles. And I've got this diagram of a triangle where I've got these lengths of sides. I suppose my picture and I think my formulas are for small angles, and maybe I should define these slightly separately if there's any negative numbers involved. I'm just looking at those lengths and wondering if people are going to tell me that, ooh, those things all look positive. You know what sine and cos and tan are. You're not learning it from that. You'll be fine. Good. Okay. Just realised I've got these like lengths, and they look like. I'll update it at some point. Okay. Pythagoras tells us a fact about distances to do with the sum of squares, which gives us a fact about sine squared and cos squared. Very important fact. Sine squared plus cos squared is 1. So this lets you translate between sine facts and cos facts, if you like. If somebody tells you that cos of theta is 4/5, then you can use that rule to work out that sine of theta is 3/5, or maybe minus 3/5. So there's a squared in there, so you won't know for sure. You might need extra information or something like that. But you can just about translate between sine and cos like that. I've got these sine and cosine facts, these facts about their range, that they lie between -1 and 1. I've got those facts as kind of consequences of Pythagoras, but I suppose you learn this in some order and it doesn't quite matter which order you learn it in. Okay. What else have I got? I've got this fact about 90 minus theta, which is on the syllabus. On the syllabus it says sine of 90 minus x is cos, and I hope you can also work out that cos of 90 minus x is sine. For small angles, that comes from thinking about what the other angle is, the other acute angle in that triangle that I showed you a moment ago. And we've got the periodicity facts. And then finally, I just want to highlight at the bottom here for this triangle. Look at that! What a triangle! Oh, I put the angles as Greek letters and the side lengths as Latin letters. The normal way to label these things is with the side opposite the corner. So I've got capital letters for the corners, lowercase letters, that's the word, for the sides, and then Greek letters for the angles. You don't have to label your triangles like this. That's just how I like to label my triangles. If I do, then I get these nice symmetric rules about areas, which is there's this rule about the area of a triangle. You're not expected to be able to work out why that's true. Just here's a fact: it's half AB sine gamma. Gamma is the angle between the sides of length A and B. There are 2 other versions of that, and then you get the sine rule as a consequence. And there's also a thing called the cosine rule, which relates the side lengths to cos. Good. Okay. Oh, hang on. So questions in chat. How do you get the -1 to 1 fact out of Pythagoras? And it's the fact that they're squares add up to 1. So the actual values of sine and cos can't be that large. If one of them, just looking at sine for a moment, if its value were 2, then there wouldn't be any real value of cos such that sine squared plus cos squared is 1. It sort of bounds the values that you can have. Sine can't be that far from 0, otherwise its square would be larger than 1. And then what would cos squared be? The real numbers to do with triangles. Good, okay. Yep, we're learning about square roots as well. Yep, good. Okay, chat is keeping up. Good. Did I miss anything else important? Do you need to know? And something that always happens when I scroll through the syllabus section is people ask, do I need to know? And then some other stuff, like some other triangle theorems or compound angle formulas. Like, no, if it's not, we would have to tell you if it's not on the syllabus. It's another triangle fact that's more advanced than these triangle facts. Then we would have to tell you. Good. It's congruence and or similarity on the syllabus. I can't see it. I think you probably do know what similar triangles are. You might use similar triangles when you're solving problems, but I think you'll be all right. How did you get sine squared plus cos squared? Oh, I have my definitions of what sine and cos were. So I have my Pythagoras theorem. I guess I divided both sides by BC squared to get 1 on the right hand side. This is a question about Pythagoras back up here. We have Pythagoras, which is about lengths, and then if you divide both sides of that equation at the top by BC squared, you get 1 on the right hand side, and you get, well, I think you get sine and cos using, my definitions up there. Good. Because it's squared, I don't have to stress about plus and minus signs. Yeah, so no radians on the map these days. I'm still talking to chat, aren't I? So no radians these days. We used to have radians until A level changed. We didn't change, A level changed. Oh, I suppose, and then we changed to match A level. A level moved the point where people learn radians. There was a review in about 2018, I want to say. So we changed to keep up with that. But it means that we can't assume that people know radians. If you look at old questions, they might be in radians. This is why we created the notes section of the past paper table. Now I have to show you that because I can't just say that, doesn't make any sense. So quick look at the notes section of the past paper table. On the map page with the coffee cup, if you go down to past paper questions and you look at that person's looking at 2012. So if you go over to notes, then you will see that, for example, question 1C, we have a note. This question was written in terms of radians. Math questions from 2018 onwards were written in terms of degrees. Option C would now be written as, and then something with sine 60 in it. And oh my goodness, question 1F has all got all these integrals and things in as well. So that year there were a couple of questions that were written in terms of radians. Nothing mathematically wrong with that. It's just these days we don't know whether people have seen radians or not. Maybe you have. So these days the questions are written in terms of degrees. Yes, you are allowed to convert to radians if you like. I mean, we know what radians are, and maybe you know what radians are, but I can't assume that you know what radians are. Okay. Right. We talked about this before, and lots of people quite like radians. So that is an opinion that you're allowed to have. Okay. Well, I've raced through looking at. Race through, it's 20 past 5. Right, I kind of raced through this next bit. Racing through the next bit, we're going to look at some of the revision questions. Like normal, I've got to vote for this. So, quickly hiding somebody in chat, plugging gradients again, which are percentage-based angles. We've got to vote for questions from the revision that you would like to look at. So if you'd like all of the revision questions, reminder that you can get those on the worksheet, which is on the Map Live page and in the description. There are 14 questions on there. The last one is a bit funny. It's got a triangle with side lengths 8, 13 and 15. And we're asked, what can you say about the angles in degrees? Questions in degrees, look. And there's some other ones we added. This year we added or modified questions 11 and 12. So I'm interested to see if people want to talk about them. I mean, you can talk about anything you like, right? It looks a bit like 13 and 14 are winning, which is predictable. And 12, but then also 7, which is interesting. 7 has got a sequence in it. That's the sum of a geometric series. So it's possible, like I said at the top, that you need the next live stream to know what's going on there. You need a little bit more information. I've combined together two topics there. As we often do, I think there's some quadratic equations on this sheet as well, and yeah, right. Okay, what else have we got? What's chat doing? Just inverse Pythagoras. I'm not sure I know what the phrase inverse Pythagoras means. Don't invert Pythagoras. That seems just rude, doesn't it? Leave him alone. He hasn't done nothing wrong, has he? Oh, maybe he has. Oh, actually, don't answer that. If Pythagoras has done stuff wrong, then maybe I don't want to know. Right. Okay. So it looks like chat wants. Oh my goodness! Somebody's put gradients in their username. That's certainly a choice you can make. Right. It's a theorem, but upside down. Okay. Right. I should say that, so someone in chat has said that they have solved question 7, but their answer doesn't match the one in the solutions, which you can get the solutions on the My Live page. You're allowed to look at them even before the live stream starts. You're allowed to look at them instead of the live stream if you prefer. If your solution doesn't look the same as the answer, it doesn't mean that you're wrong. There's sometimes more than one way to approach them. You might write something totally different from me when you try to do the questions. I've tried to pick a version that I think is the easiest to explain, because the job of the solutions document is to explain what was going on to people who have had a go at the question. Your way might also work. Maybe I even considered it for the solutions document, but usually I've picked the one that's easiest to type up for the document. That's not laziness, that's efficiency. Right, 13 has won this poll, hasn't it? There we go, 13's won the poll. Okay. That's Rosie telling me that, but inverse Pythagoras is Pythagoras upside down? Okay. Divide everything? Do you take Pythagoras and divide by a squared, b squared, c squared? Or do you flip 1 over b squared plus c squared is 1 over a squared? I kind of want to know now. Alistair, I haven't updated the flashcards this year. They are the same as previous year, which is a bit sad because when I had a geometric series going, there were originally 40 something cards, possibly 40 cards, and then we added about 20 more, and then we added 10 more, and then we added 5 more, I think. And I should have added 2.5 more, but I think I broke the sequence at some point. Right, okay, that's chat. Okay, so we're going to have a look at questions 13 and 14 in that order, and then scroll back up again. Time to do some maths. Okay, so 13 wants us to prove something. We're given the cosine rule and the fact that cos alpha is between -1 and 1, and we have this triangle with side lengths A, B and C, where A is bigger than B is bigger than C, and they're all positive numbers. So our aim is to show that B plus C is greater than A, which is called the triangle inequality. There's this big comment in brackets that's almost as long as the question, if not longer. But we're told to use the cosine rule. Now, I want something for B plus C that has A sort of separate from the B plus C. So I think I want to start with A squared, that version of the cosine rule. There are sort of 3 choices that you can make, I suppose, depending on which angle you look at. So different things are, different choices are available. But I think I want this one because it has A on one side and B and C on the other, and I'm trying to show that A is less than B plus C. In chat, the flash cards, it's a series of flashcards that you can get. I've got them here. You can get these off the website if you like flashcards. They are things for you to revise. For example, if you see this, something like this, a sum, the thing you're supposed to remember is that, oh, that's a geometric series, and the sum is this. So it's a flashcard where you shuffle them, and then you get a way to sort of revise things, while also practicing your sort of recognition of things that are on the syllabus. I picked the geometric series one because that's something that's coming up in question 7 in a moment. I used to update them every year, but now I think we've reached their final form, so you can get those on the MAT website. I think they're on the MAT Live page if you're over there. If not, yeah, maybe you have to scroll down, but I think they're on there. Good. Okay. You do not need to know. They say the extended sign rule involving 2r, which is something like the ins, or it's one of the radii, one of the circles. None of that. Anyway, what am I doing? I'm trying to do this. Okay, so I have this fact about a squared. I'm in quite good shape because, well, b plus c, and I can see a b squared and a c squared and a 2bc. So I'm thinking maybe this is a bit like b plus c squared, and this is like a squared, of course. It says a squared. So I think my aim is to show that this is less than or equal to, yeah, my aim I think is to show that this is less than or equal to b plus c squared. And I suppose that's true because cos alpha, ooh, handwriting, cos alpha is greater than or equal to -1. Do I mean less than or equal to 1? No, I mean greater than or equal to -1. So this expression is small. It's not as large. Even if cos alpha is a very negative number, it's not that negative. So this can't be as large as plus 2bc on the end, which is b plus c squared. So now I'm happy. I've got kind of what I want. I've got a squared is less than or equal to b plus c squared. And then two things to check. Check that square root on both sides is okay. So I think because these are positive numbers, their squares being in that order really does mean that the numbers are in that order. And then the other thing I want to check is, why not equality? Why can't they be equal? Why can't it be the case that these are equal? And I suppose it's if they're equal, then cos alpha is -1, which only happens for 180 degrees, which is not a realistic angle for a triangle. Get this kind of non-trivial triangle. Why b plus c squared? Well, I was aiming for b plus c. There's another one. There's another fact like this involving b minus c that you could prove. You know that I've used this bit that cos alpha is greater than or equal to -1, I think, to say how large is this term? Well, it looks negative, but watch out, it could actually be a positive number. It could be large and positive if cos alpha is negative. And the more negative cos alpha is, the larger this thing is, the more positive it is. What's the limit? Well, if cos alpha is very negative, like -1, it's as negative as it gets, then this is positive. 2b. You can do something else as well. So you could say that this is less than or equal to b squared plus c squared minus 2bc, because because cos alpha is I suppose less than or equal to 1, where you say maybe I mean greater than. Ooh, what do I mean? Okay, worst case scenario, the most negative that you can make this expression is like you lean into this minus sign out here. Yeah, that's right, 2bc, that's huge. Cos alpha, I'm going to make that huge as well. And if you make it huge, then you're making it equal to 1. So this would be, wow, b squared plus c squared minus 2bc, which is b minus c squared. I probably want to write, yeah, b minus c squared, because that's a positive number squared. So I suppose a is greater than b minus c. This is another one of the same expressions. You get symmetric expressions involving a and b and c. You can choose which side is a. Yeah, what did the minus 2b? So what did the minus 2bc turn into plus 2bc? And I guess James John Rowe was also asking why not minus 2bc b minus c here. And it's because there's two routes you can go. There's a branching path here. You can use the fact that cos alpha is not that positive, in which case you end up with this fact. or you can use the fact that cos alpha is not that negative, in which case you end up with this fact. So I'm using the fact that cos alpha is greater than or equal to -1. That gives me a sign of this, some inequality here, and it gives me a change of sign. If you like, we can build that up from this fact. So cos alpha is greater than or equal to -1, so b times c times cos alpha is greater than or equal to minus b times c. I should put the 2 in as well. 2 minus 2bc. But then, actually it appears in my expression with a minus sign on the front. So I should write minus 2bc cos alpha, scroll, almost got it, less than or equal to 2bc. So you see this minus sign at the front, you can think of that as changing the direction of the inequality and appearing on the other side as well. I picked this one because I wanted a b plus c squared, because there was a b plus c in the question. Yeah. If you like the case when alpha is 180 degrees, K in chat says if alpha is 180 degrees, then you don't really have a triangle, you have a line that you have drawn twice. Some people count these as a triangle. They might call them degenerate triangles. I think the name speaks for itself, really. Do we use the assumption that A is greater than B, greater than C? We do a little bit. Not really, I suppose. Yeah, not really. Maybe the question doesn't need to put them in this order. It's nice that they're all positive. But yes, you're right, we don't need, this is not just a fact about the longest side. Yeah, maybe the question should be, it's not really a fact about the longest side. On screen I can see it says the longest side. Maybe we just need, maybe it's helpful if I just say that okay, next version might say all three of them are positive, that's all we need, and instead of referring to A as the longest side, we have to do the other one. Okay, yeah, we didn't really use that inequality. We would have used it if we were going for this b minus c thing, perhaps. Over here, I'd quite like, maybe I'd like b to be greater than c over here if I'm planning to take some square roots of this fact. But if you go down that route, then you're looking at b minus c kind of fact. Nothing wrong with that, I suppose. Good, okay. What next? That's 13. My strategy for questions like this, in a kind of problem-solving sense, is, well, write out something I know, and then try and write down true facts. I have a tendency to try and jump to conclusions, so I have to make sure that the steps I'm doing actually make sense. I guess I'm so keen to be done that I would like to write down b plus c squared, and I have to sort of make sure that I have some reason for each step that I'm doing. But I'm always motivated by what we've got, which was the cosine rule here, and where we want to go. Over the years I've got better at spotting the kind of vague shape of where we're trying to go. That for me it's about b and c on one side of an inequality and a on the other side of an inequality. So I knew I wanted the version of the cosine rule with a squared on one side. Why did the cos disappear? Well, if you like, here's an inequality where cos appears on one side and not on the other. And as a consequence of that, you get this inequality down here in the bottom corner, which you could read as saying, when you see this thing with cos alpha in, inequality without the cos alpha. I mean, you'd be happy, I think, with this true fact. There's no cos on the right hand side. I've replaced it with a number 2, and then done some adding, I suppose, and made that look like a 5. But you can use these inequalities to simplify expressions. Inequalities don't have to make your life worse, they can also make your life better. That's a message to those who aren't enjoying inequalities. Good, okay. 14 is about a triangle with side lengths 8, 13 and 15, and we're asked about the angles. I suppose, given 3 side lengths, the thing I would like to think about is the cosine rule, but I don't know which one. I don't know which angle we're looking for. So I think I'm going to work out a squared, b squared and c squared in some order and see what I can do. Let's see what I can do. So a squared might be 64, b squared might be 169, and 15 squared is 225. Now, can I see anything going on here? No. I think it's time for the cosine rule. I might need all three versions. It's looking like that. So, what am I calling these? A, B, C. Well, I've labelled my triangle the wrong way around. Never mind. Not actually incorrect, just not the way I prefer to label triangles. Anyway, 64 is b 13 times 15 cos alpha. Anything going on there? I might have to work some of this out. Oh, I'm not looking forward to that. Other ones? So because I've got these squares, I can write them in various places. Can I do this while talking at the same time? I'm not sure I can. Here we are. I've got three versions of the cosine rule. Is this one B? With angles alpha, beta, and gamma. The question wants me to find one of these exact value in degrees, so I'm hoping that one of these simplifies a bit. And I'm coming to terms with the fact that I'm probably going to need to calculate some of these. Reluctantly, I'm going to start with the first one. So 105, 330. Right, okay, we're going to go this way. Cos alpha is, what is this? 105, 330. So minus 330 divided by, what is this? 33, 390? That doesn't look like anything. I don't know anything like that. That doesn't look good. 105 minus 225 would be minus 120. Good chance that I get one of these wrong and have to come back to it. 80, 120. 240. No, that's good. That's minus 1/2. I have strong feelings about that one. Okay, I'm not going to work out the other one because I know that for cos beta to be minus 1/2, I must be looking at 120 degrees. Should be minus 2b c cos alpha. Probably. Thanks, chat. If I got the cosine rule wrong, yeah, I do. Maybe I do this to test you? Is the tan rule on the mat, says someone in chat? No, I don't even know what that is. I've got the sine rule, the cosine rule. You divided one by the other to invent your own new tan rule, or is it a thing that you learned before? Whoops. Still 120 degrees. I made two mistakes. Did you spot the second one? They do need a minus sign. Thank you, everyone. Why don't I just use pi times? No, never mind. Almost read out. There we go. Oh, Georgina, you can tell them about the PhD. What does Georgina say? Fancy Oxford word for a PhD. Yeah, there you go. I think DPhil sort of makes more sense, right? It stands for Doctor of Philosophy, whereas PhD stands for Doctor of Philosophy, but backwards, like Philosophy Doctor or something. Right, okay. So other than minus signs, I think I've worked out that tan beta, cos beta, what am I talking about? Cos beta is 1/2. Do I like that? Yeah, I think that's all right. That means it's 60 degrees. Right. What am I doing? Minus sign, and then I got minus sign, and then I got thrown by my cos values. Ooh, I'm not having a good one here. If you're playing along at home, I hope you're getting minus signs more accurately than me. Reset the counter. I've made another minus sign error. Doctor, oh no, yeah. Right, good, okay. Where next? We've got our 60-degree angle in this triangle. The other ones don't look like they have nice values at all, even if I get the minus signs right. Yeah, I was about to work out that the triangle had 3 obtuse angles. That would be impossible. Maybe I'd have spotted that. Good. Let's have a look. What next? Yeah, I wish that. Sort of wish. There's a comment in chat about maths degrees. Sort of wish that they were the doctor on my kind of Doctor of Philosophy, because that's what the degree is. This chap Georgina was. Sort of wish it was Doctor of Maths. Quite nice to be a Doctor of Maths. The Maths Doctor will see you now. No. Doctor of Philosophy it is. I don't know anything about philosophy. Right. Where next? There were some requests in chat for 12, and then we'll have a quick look at 7, because I know Kay in chat wants to do this. Ooh, Jonah wants me to add the equations together. What happens if you add the equations together? Do you get a new kind of super cosine rule? Probably not, but maybe. What do you get if you add them all together? You get a copy of the squares, and you get some sort of fact about the angles. I don't know what happens if you add them all together. Jonah says we need to add. Ooh, okay. Just for fun, what happens if you add the equations together? I'll cancel this. A squared, b squared, c squared, but on the right I've got 2a squared, 2b squareds, and 2c squareds. So what's this then? Am I going to commit to which one's A and which one's B? I probably should. So this is BC cos alpha plus AC cos beta plus AB cos gamma. So it's some relationship between the sum of all the squares and angles and side lengths over here. It's pretty good. Quite like this fact. I don't know if it's got a name. We've added together the cosine rules and got some nice symmetric fact about cosines. Thank you for joining the MAT livestream, where we sometimes just add all the equations together. That's the correct answer for a thing. There's this Assassin's Creed level where there's some sort of mysterious code and there's lots of different buttons you can press, and the solution to the puzzle is to press every button. Just press every button exactly once. Switch them all on. And if you switch them all on, then you solve the puzzle. And sometimes doing maths, I think about this, I think about it too much, because sometimes you add all of the equations together and you go, ha! I added them all. I switched them all on. I want all of the equations all at once. And then you get something nice and symmetric out of the result. But anyway. Right, maybe I've spent too much time. Okay. Chat's going places, I think. Right, okay. Question 12, working backwards. Working backwards now, because 12 got lots of votes as well. This is one of the new ones. Do I want to do 11 first? Maybe I want to do 11 first. There's a small difference between 11 and 12, which hopefully you spotted while doing them. You can just do question 11 twice. So in question 11, we're given side length AB of a triangle. We're told that it's 8, and we're told that side length BC is 7. And we're told that this angle is 60 degrees. ABC is 60 degrees. All very good. We're asked for the remaining side length AC. This is fine. This is a classic kind of cosine rule exercise where we know, if you like, a squared and c squared and 2ac, and we know the value of cos beta for the angle in between. We're going to be fine. We're going to find the square of that side length. That's all right. So I'm just going to write cosine rule. Everything's fine. Question 12, we're given almost the same information. We're given the side length AB. We're told that it's 8. But this time we're given the side length AC. We're told that it's 7. And we're told that this angle over here is 60 degrees. It's the same angle ABC. The problem this time is that there are 2 solutions. The question says find all possibilities for the remaining side length BC. And there are two possibilities. There are sort of two pictures that you can draw, one like that and one like this, of two lines that are the same length. They're both length 7, that get you to somewhere on this 60-degree slope from B. You can do this using the cosine rule, but the cosine rule now becomes a quadratic equation with two different solutions. So still the cosine rule, same approach, but now different emoji. We're now in a slightly strange case where we have two solutions. But I still want to write down, side lengths. It's just the only thing that's changed is over here I have b squared equals 7 squared plus 8 squared minus 2 times 7 times 8 equals 60. That's kind of a quadratic equation because b is squared, but I mean, come on, it's a quadratic where you're going to have plus or minus varying a positive solution, don't you? Over here we've got 7 squared is b squared plus 8 squared minus 2 times 8 times b times cos 60. And that's totally different. That's a quadratic with b squared and b in. That's b. And it's got two solutions. I mean, why not? It's quadratic. Two solutions, one solution, no solutions. So sometimes, for some numbers, versions of this problem might have two solutions or one solution or no solutions, because that's what quadratics do to you. And also geometrically, we've got this line AB, and then we've got this 60-degree slope. And it might be the case that as you reach out, there might be, if you make the number 7 a bit smaller in this problem, there might be no way to reach that line. There might be two if you look further afield. You might have two places you can go. They are either side of the perpendicular bisector. There's a symmetry here that the perpendicular bisector is your shortest route to get to that 60-degree line. You've got to be at least that long if you want to find this point C. So when we set up this question, we've got to make sure that 7 is larger than that perpendicular bisector, whatever it is. But then there's a symmetry where you could be on the left or the right of the perpendicular bisector. So you end up with a couple of solutions in different cases. Right. Good. What does chat say? Oh, I haven't been looking at chat for a second. Let's put it back on screen. Did you spot these two different cases for this one on question 12? Add all the equations. Good. Sine will naturally be two solutions. Yeah, well, I wonder which question that was. Sine rule I have as yeah, I gave you lots of angles. Yeah, thanks. Somebody set their username as 34 because I once made a mistake involving the number 34 and I'm not allowed to forget it, apparently. Good. And somebody met me at National Maths Summer School last year. I'm not doing it this year. Timetabling clash. I enjoyed it last year though. Summer schools, loads of them. I've just finished 3 in a row. I've got 2 more coming up later. Last year I did 7, which was probably too many summer schools. Right, there you go. Kay has had time to fix their problem, but we're going to go and talk about question 7 in a second. Yeah, so for a question, this is a good, I like this question a lot. Thank you, Anonymous. For a question of this format, question 12, but with different values of 7 and 8 and 60 degrees, for want of a better word, the case where you get a repeated root is, on the one hand, where you get discriminant equal to 0, but on the other hand, it's where you have a right-angled triangle, like you say. It's the case where it is, the number 7 is chosen just right to be this perpendicular bisector. If you like, that's a kind of unique solution. These 2 points, as you decrease the number 7, these points get closer and closer towards the perpendicular bisector point. Closest point. You try to find closer and closer points on this line to A, and they move together until just at the kind of case where you get one solution is the repeated root. Said differently, if you go and calculate the discriminant of this quadratic using, I suppose you're going to have to use the letter C or something instead of 7, then everything works out the way you said. Get a right angle triangle. No forgetting. Right, good. Okay. Where did the second solution come from? Well, here's a quadratic. Let's go and solve it together. I seem to have used the letter B again, even though it's the other side of the triangle now. That's a little bit clumsy of me, but you know, I think I've got away with it. Let's find out. So minus. Oh, I'm going to need to know what the value of cos 60 degrees is to do this question. That's going to reveal that I have to think when I do that, which is, oh well, unavoidable, I suppose. Thinking, eh? Now I also have to think about 64 take away 49. Oh, am I going to get that right as well? If I got both, that'd be good. If I've got both, checks notes. No way have I got both of these right. Oh, yes, I have. I have got both of these right. So there are two solutions to this, right? We can factorize this quadratic. B could be 3 or 5. Interesting, the symmetry appears to be that this perpendicular bisector, this point right in the middle, this length, which is not really part of the question, but is like, if you had to find this kind of perpendicular bisector, that length is 4 because of the 60 degrees and the right angle down here. That's cos 60 times 8. That's the hypotenuse for a perpendicular bisector line. I'm saying bisector a lot. I don't mean bisector, do I? What am I bisecting? I just mean drop a perpendicular to that line. Oops, sorry. 4 is the average of 3 and 5. So if you change the value of 7, then these things get closer and closer together until they meet. Good. Okay, well I enjoyed that. That was a fun diversion. Somebody's asked what happens on the Unique Math Summer School, and we've got several things going on. But one thing that people remember is that I set lots of different problems where the answer is always 10 choose 5. I don't tell people that, and then we go through the answers and it's always 10 choose 5. And some people find this very memorable, let's just say, which is what I wanted, for you to see different problems and remember them as well. Now that I've said that, if anyone's in year 11 and you're coming to Unique next year, maybe you're watching this video at the start of summer 2026, then forget I said that. Probably I've changed all the problems now. Probably it's not 10 choose 5. That would be weird, wouldn't it? Good. Okay, we have been through some revision notes, questions 13, 14, 11 and 12. If you would like this, then you may need to rewind the video to see 13, 14, 11 and 12, which you're allowed to do even while we're recording it. I am waffling. I should be doing question 7. Let's go and have a look. Question 7 combines our stuff on trigonometry with a series where I'll do the kind of solution, I suppose. This is a geometric series. If that doesn't mean anything to you, then good news. Next week I will tell you exactly what that means. It's got, I would say, first term is 1 and common ratio negative sine squared x. So the sum to infinity. There's a formula for it, which if you haven't seen it before, I'll teach you next week, is 1 minus, what am I doing? 1 plus, am I wrong? No, I'm good. 1 over 1 plus sine squared. Good, yeah, I'm panicking because I thought that was supposed to be a 1 minus sine squared, but it is a 1 plus sine squared. For some reason the question says do that in terms of cos, and I really don't know why. I can't remember why I did that, sorry. Just 1 over 2 minus cos squared. Using the fact that sine squared plus cos squared is 1, I can rewrite that sine squared as 1 minus cos squared. I have no idea why I did that, sorry. There's a weird trigonometry fact at the end. And because for this to work, I need the common ratio to be strictly less than 1 and strictly greater than -1 as well. which again, if it's not a fact you know, then good news. We're going to learn about sequences and series next week. You could get the worksheet ahead on the MAT Livestream page if you want to learn that. Good. Do you lose marks for using double angle and addition formulae? No. I mean, if a question tells you to do something and you do double angle formula and addition formula instead, then you will find that you don't get the marks because you didn't follow the instructions. But if you want to use the fact that you know some extra things, then that can definitely help you to get marks. I mean, if you can find a way to use it. I can't see a way to use double angle formula on any of the questions that we've been looking at so far. So maybe I should just know. I think the answer is just no. You don't lose marks for using double angle and addition formulae. Good. Okay. Right. Okay. I suppose a different approach would be to rewrite some of the terms in that geometric series. So maybe you see the 1 minus sine squared at the start and you decide to write that as cos squared. And then maybe you see the sine to the 4 minus sine to the 6 and you decide to write that as sine squared x, or sine to the 4x I suppose, times 1 minus sine squared is another cos squared x. So that's quite good. What's the next one? I get the next terms are sine to the 8 minus sine to the 10. So you could write that as sine to the 8x cos squared x. There's always a 1 minus sine squared going on. If you do that, then good news. You have common ratio, you have first term cos squared, and you have common ratio sine to the 4. And then you get to use 1 minus sine squared one last time on a difference of two squares kind of situation downstairs to get this, which is the same formula that we had before. So happy face. These agree. You use the sum of the squares on the sum of the pairs, you'll find that downstairs you still have the same pair of terms. 1 plus sine squared. Good. Was that the expression I've written for the sum, not for the sequence? Yes, it's a sum in the question, look. It's got all minus and plus signs in it, but that's a sum. What did the question say? As a single expression, yes. Yes, all minusy plusy signs, not a sequence. Good. Cool. That is amazing. That's like actively nerd sniping, isn't it? Because it could be anything, but I know what number it is. 4x4 magic square could be anything, right? Good. This is amazing. Right, okay. Right, well, is there anything in between all of the people saying 34 in chat? Is there anything about that I need to read that's useful for math people? If you put plus signs in, that's good. If you put plus signs, then you get this, which is also interesting. But you still have this same problem that you shouldn't let people set x to be 90 degrees because then your ratio will be 1, which again you don't want. For the sum of the GP, we need your GP is this. So where's cos to the 4 come from? That's my suspicion. I've got something with cos. I've got some cos. I don't think it's equal to this geometric progression though. Okay, I agree with the cos squared, but then I don't see where the minus cos to the 4 has come from. I've got something similar on here, but I've had to do something a bit different over there. Okay, right. Amazing. All right, good. Okay. We're approaching a fixed point. Right, it's 6 o'clock, which, as we all know, is time to take a quick breather to think about what we're all doing here and to get ready to move on to some math questions. I'm going to put a math question on screen. I'm going to take a break to drink some water and look away from a screen for a bit. If you've been looking at a screen for the last hour, this is a reminder that you're human and you Remember to drink water and look away from screens occasionally. Yeah, so in chat somebody's suggesting that we do the 1 plus sine squared plus sine to the 4, which I think just works in the same way. It's kind of nice, it's got plus signs instead, so it's slightly better. Oh, and then it's 1 over 1 minus sine squared, which is the one that I wanted, because then it's 1 over cos squared, which is kind of nice. That suggests that, well, it will get really close to 1 over cos squared. I want to see that. Do I want to see that? We could Desmos it. Quick Desmos break. Remember, you're a human, and every hour you should remember to check Desmos. So the thing that we've got in the question was 1 minus sine squared. I remember that Desmos doesn't like things where you put the power. It wants you to put power over there. Is this good? Is this good? That's not too bad. So if I do a few terms before I get bored, then the thing we've worked out is that this is the same thing as 2 minus cos x squared. Ah, so I'm not doing very well here, am I? The blue curve and the red curve look nothing like each other. Have I missed a minus sign? Wouldn't be the first one, would it? Or do I just need more terms? Do I just need more terms? Do I want a bracket around here? Oh, quick break where I put brackets in all the wrong places. I'm kind of surprised by how bad that is. Oh, it's getting better. It's getting better, but not a lot. Was that good? Quick check. If I delete those, does it get worse? It does get worse. Okay, so this red line is getting a bit, it's kind of close to the blue line, but not really. And especially round here, oh, is this the pi over 2 place? So pi over 2, 90 degrees, is really quite bad, and it's not getting better. Which I think is why I've excluded it. That's never going to get up to that point up there. Good, okay. So it's interesting, the expressions both check out. The expressions are both fine when x is 90 degrees. Ah, no, they're not. This one is really not fine when x is 90 degrees. This is the thing, isn't it? If I put in an extra one up to 12, then it's like that. So this is going to bounce up and down. I'm getting slightly better as you go. Getting closer and closer to the blue line, except right at 90 degrees. Degrees, please. Ah, that was a mistake. Right at 90 degrees, it's going to split between 1 and minus 1 as I add on more terms into this sum. Okay, fun times. Combination of trigonometry and geometry series. Yeah, that was fun. Good. Okay, there's a math question on the screen. I would like chat's feedback. How are we going to approach this question? It asks us for the largest value taken by the function, and then there is, oh my goodness, it's a quadratic involving sine and cosine, maybe. Is that even a quadratic? I don't know. Not really, I suppose. It's been wrapped in brackets and a big square. Cookie asks for a book recommendation in chat. I've recommended Stephen Siklos's book before. Let's recommend it again underneath here. It's called Advanced Problems in Mathematics. And it looks like this. It's really good. It's free online for, not involving piracy. You can just get Advanced Problems in Mathematics Preparing for University. That's a free book. It's just a thing that you can do. You can also pay for a physical version if you like. But there we are. Okay, what are we up to? People are telling me how they would make progress with this. Oh, has Georgina recommended a book as well? Let's have a quick check. It was, yes, well done, Georgina. How did you know? Okay. Complete the square says everyone. Does everyone say complete the square? People are switching to cosine, and people are finding hidden quadratics all over the place. I thought it might have involved quadratics. It's the fact that there's a squared term but not a cubed term that gives me confidence that maybe we could converts to some sort of quadratic expression. If we do that, so if we, I don't know, so cos squared, it's all on the flashcards, I think, that you might, kind of spidey sense that we want to convert this. Let's start again with better handwriting and correct maths. So that sine squared, you might want to convert to cos squared. If you do that, then you get something like this, which is not that bad. It looks, this is inside the square, but it's not that bad, is it? What we could do is we could think about the quadratic inside the brackets. I guess it involves cos theta, we'll be careful. And also this squaring means that, up to you, you could not do this step of putting, I put minus signs everywhere. I've been really careful to put minus sign everywhere. Up to you whether you do that or not. It doesn't matter in the long run because we're both going to square this final thing. I prefer to have my quadratics looking like this, I think. Maybe I could complete the square. People would like to complete the square. Make it fully in cosine, complete the square. Maybe I don't even need to think about this with u instead of cos x. Maybe I should just write cos x and complete the square anyway. Maybe I should just get on with doing it like that. So what would that be? I suppose this is 2u minus 1 squared. Careful. 1 minus 6. Is that true? So then, what do I want? I've got this, but it's actually all squared. And the question is, I can change the value of u. U is equal to cos x for me. I can change the value of u. What would I like it to be to make this very large? Well, I could try to make this bracket really large, but this minus 6 is weighing me down, isn't it? The largest I can make this bracket is 2. Take away 1, it's 1, which is not very big. This will get up to -5. Whereas if I make this very negative, well, I can do that by making the square bit inside the bracket 0, and then we'll get down to -6. You have two choices. When you're trying to make something large inside brackets that's going to be squared, you can either make the thing inside the square very positive or very negative. Either works. Whichever one you can do in a more extreme manner will give you a larger square. You can make it maybe 3 or -4. I'll take the -4, please. It's better for squaring. It gives a larger answer. -4 or 7? Oh, I think I'll take 7. 7 squared, further from 0. So I think I would say something like this term in brackets is at most 1. So this thing is between -6 and -5. And then it squares between 25 and 36. So I think the largest I can make this is 36. Good. And people in chat seem to agree with me. You could differentiate. I wouldn't recommend differentiating, and not everybody who's watching this can differentiate that. So good news, I don't recommend it, even if you can. Questions are often like that. You could differentiate if you really wanted to. Oh my goodness, that would be no fun. And if you do know maths that's not in the syllabus, like the compound angle formula or the extended sine rule or how to differentiate cosine, then partly I would encourage you to remember that the test is designed so that you can do the question without knowing those things. Good. It's not a problem to differentiate, I just think it looks tricky. Like you'll do a lot of work. You'll end up with the same answer. But also when you differentiate, you find the minima as well as the maxima. So you'll need to think again at the end. There's nothing wrong with calculus. Calculus is fine. I'm trying to talk to the people who want to use calculus to say, knock yourself out, try it with calculus. But also talk to the people who don't want to use calculus to say, you'll be fine. Right, good. Okay. let's look at another. I think I'm going to skip this graph sketch one. So we've got here cos squared x is cos squared y, but I think chat's got very good at square root sort of things. Let's put it all on screen. There's 5 options, you see. I think chat's pretty good at this sort of thing, where cos squared x equals cos squared y. That means that either cos x is plus or minus times cos y, and then those cases are not too difficult to handle. You just have both of them. You have 2 possibilities. If you like, you could move cos squared y on the left, do the difference of 2 squares, and then get 2 brackets multiplied together where you want either the first bracket or the second bracket to be 0. That gives you kind of 2 sorts of graph. I think it's probably loads of cases where these are the same. Not E, just because it looks weird. Let's do this short question, and then I think it's time to move on to some longer questions. I was keen on C. Why does f max value 36? Well, I think you can make the thing inside the brackets. Right? Question. You can look back at squares very quickly. So very quick rewind. I stopped here because this 2u minus 1 is between 0 and 1, which is surprising perhaps that it's got an upper limit, but that's because, well, you can't make u that large. Well, I suppose actually I'm wrong. I'm wrong, aren't I? I've been tricked by my own trick. I was very careful with the squaring, but I've just realised that I could make u, as well as making u 1 and getting boring or 1 squared, I could make u be minus 1, and then I get minus 3 squared. So something I said earlier was wrong. Thank you for the rewind, because this could actually be as large as 9. So then, after I subtracted 6, yeah, okay, this thing is between -6 and 3. We're going to square it, so we want the most extreme value that we can put into that square. So I get lucky, and the answer is -6 in the end is what you should put into the square to get 36, option B. But I was wrong about the other limit, I think, because I missed that you could be a very negative number squared to give a very positive number squared to give a very positive number, and that extreme or sequence of extremes might be different from giving a large positive number squared to give a large negative number squared, which is not as large as the other one squared. Cases within cases. Oh dear. Right, okay. It's got this structure, right? Number minus number squared. Minus number squared. Okay, it says it twice. Minus number squared. Minus number squared. I got that second one. I analysed the second one just right, but I got confused by the first one. This is reflection. This is looking back on my successes and my failures, which no one can accuse me of not looking back on my failures. Right, okay, let's do another one. Here's another one. Thanks for the reset. This one's about cos to the nx. Oh, is it too obvious what to do on this one? I don't know. Cos to the nx plus cos to the 2nx. And we're asked how many solutions that's got, depending on the values of n. Different values of n, it might be different. In some of these options, this says 3 for all n is one of the options. So maybe it depends on n, maybe not. Is it too obvious what to do with this? I don't know. Maybe not. I said before that the highest power was 2, so I wasn't worried. Here, the highest power could be much larger if n is larger than 1. But maybe we're not that worried. Yeah, maybe we could factor or something. Nee in chat has one last question about the maximum value, and it's because u is bounded. U was secretly cos x, and I sort of wish I'd left it as a cos x so that you could have seen that that's bounded. You're right that 2u minus 1 squared could be anything until you remember that u is between -1 and 1. Yeah, so in chat, one person wants to make a substitution and one person wants to factorize. Bring out a factor of cos nx because it's common to both terms. seems nice. At this point, I really want to give it a name, but maybe that's just me. Let's try not. Rosie in chat has got that message, which is a little bit different because they've not got the minus signs, and they say that this makes things work out much better. I'm not going to go back and check it. But I thought you'd like to see that as well. Thank you, Rosie. Right, now there's people up above telling me to factorize it like this, and then either use cos the nx is 0 or 1 plus cos the nx is 0. This first one looks to me like it says that cos x is 0. I'm happy that that's got a couple of solutions in that range, 90 degrees and 270 degrees. Okay, so at least 2. And then this one, it doesn't really matter what value of n is, right? N is an integer that's 1 or more, so yeah, I'm fine, okay, good. Over here though, it's not clear to me whether I want, you see, if n is 2, then this has definitely no solutions because it's 1 plus a square, and also if n is 4, this has no solutions because it's 1 plus cos squared squared. If n is 6, then it's 1 plus cos cubed squared. In general, if n is even, then I have a problem. N even, problem. If n is odd, then I've got something. Obviously, I want a negative number because I want cos to the n to be -1. Possibly, I should have written this out with a -1 on the right hand side. That's how roots of quadratics work, or working out brackets. And -1 is a pretty funny number to have as your power because, well, what did you do a power of? It wasn't 2 or something, was it? It was probably -1. So in this case, I want cos x to be -1, I think. And I want n to be odd so that I have an odd number of minus signs. I have to think about the magnitude of the number there to realise that, actually I do know the nth root of -1. It's funny to think about that. I know the nth root of -1. If n is an odd positive integer, I don't know the square root of -1, but I do know the nth root of -1 if we're talking about a positive integer. Right, what are we doing? Cos x could be -1, and it does that if, when does it do that? Oh, just at 180 degrees, but we get a sort of bonus solution only when n is odd. So I think I've ended up with 3 for odd n, 2 for even n. And that looks good to me. Ooh, there's some factoring in chat. Let's have a quick look. Put chat back up. What's chat been up to while I was solving? Yeah. Can't do cos to the nx is -1 for even n. Good, like it. Cos to the nx is 0 as always. Yep. But then something depending on that. Pi, because I said 180 degrees and they're a radian in Joya, and that's allowed. What's this factorize? Oh, is this complete the square sort of stuff? This looks like complete the square kind of stuff. If you set a very long username, then it does tend to slightly overlap your message, but that doesn't seem to be stopping people, so there we go. If you complete the square, then you get, well, I guess maybe you're going to carry on and solve this thing. And I think you'll meet me down here at 0 and -1. I'll see you down there. So odd n has 2 solutions. How come it's not 2 for odd and 3 for even? Yeah. So I say when n is even, you get no more solutions. So just these 2 when n is even. So 2 for even. But then 3 for odd, because you get this bonus solution only when n is odd in this last line. It's always 180. I like 180. 180 is good. Why can cos the nx not be -1? Well, if n is even, then it's anything to an even power is always positive. Because anything to an even power, x to an even power, like this. So here I've got some number, don't care what it is, could be a cosine kind of thing or not, to an even power is always the same thing as x to the m squared. which is positive or 0. It's definitely not -1, because nothing squares to -1. So something I'm worried about is even powers trying to be negative numbers. It just doesn't happen. Okay, it's good to look at the short questions, but we've also got a request to look at long questions. And we've got a good bit of time here. We've got 40 minutes left on the clock for the stream. So quick look at them on screen, I think. And there's hints in this PDF as well. Here we are. So there's one question about this on the sheet with this circle inside a triangle. I think it's a right-angled triangle though, so I think we're going to be fine. We're asked for the coordinates of Q, and then we're asked about the areas. So it's a good question. Areas inside the triangle but outside the circle. There's kind of 3 of them. One of them is not really in the question because it's easier to calculate. There are 2 others. And there's this other question, scroll past the hints, about a circle balancing on top of a parabola. So the first one was from 2007 and the second one was from 2012. Could you let me know in chat which one you would like to see? And while you're voting, there is a request in chat for one more re-explain, one more reload on the previous one. So I'm going to split and see. So one more. Okay. Different numbers of solutions last time. Over here, for any value of n, you always get a couple of solutions because, well, for any value of n, cos x could be 0, and then that works. So 90 degrees and 270 degrees always work in this expression because both terms are 0. And then the other question is, could the terms cancel each other out? If n is an even number, the answer is no, because both terms would be positive. We'd have the sum of 2 squares, and the sum of 2 squares can't be 0. Well, unless the things are 0, which we already thought about. So if n is even, then that's it, because they can't sum to give something else. That's what this bracket is describing. It's describing the sum of the terms, and not just the case that both of them are 0. That they genuinely sum to 0 without being 0. If n is odd, though, everything's up for grabs. We can still play this game. If n is odd, like 1 or 3, well, when it's 1, we're literally looking at cos x equals -1. When it's 3, we'd be looking at cos cubed as -1. The only number that cubes to -1 is -1. And similarly, if n isn't any other odd number, the only thing that, when raised to an odd power, gives -1 is -1 itself. If you like, think of the graph of x to the 5. It only goes through -1 once. X to the 7, same property, only goes through -1 once. Okay, that's the reset. There are some votes in chat. Oh right, I should maybe have done a poll. We'll do a tally. We'll do a tally. There was votes for the second question, and then the first one, and then the first one, and then the first one, and then I saw vote for, what was that? Four for the first one, and then look away now if you don't like improvised polling, and then 7, and then 34, and then 2007. So I think 2007 has got slightly more votes, so we'll do that one first. And we might have time to have a quick look at 2012, which is not as bad as it looks. Part of the reason that the 2012 one looks bad is, well, partly because I translated it to be all in degrees. The modified at the top of this question is because this question is from 2007 and was written using radians. These days would be written using degrees. So I rewrote it. Bunch of votes for 2012 at the last moment, but I've scrolled up now. Okay, and a vote for both. Thank you. Right, good. Okay, let's try and do both. Seems like a good aim. Here's what we're going to try and do. We've got a triangle. It's got center 1, 1. That's not marked on our picture. It's got radius 1, and we've got the x-axis, and the point R is on the y-axis, so there definitely is a right angle between the x-axis and the y-axis to mark onto our picture as well. I'll do a version over here, you'll see it in a moment, but if you're playing along at home, I would encourage you to mark in the right angle in the bottom left corner between the x-axis and the y-axis, to mark in the centre of the circle at 1, 1, and we'll draw in some more lines in a moment. I'll show you where I might put them. We've got areas that are going to come into the question later, A theta and B theta, marked in the picture. I think I'll add them in when we get there, because the first part of the question is just to find the coordinates of Q, that point up. You can see it at the top there, where the line meets the circle. And we're going to find sort of the gradient of the line PQR, and we're going to find the equation. Once we find the gradient, that'll be fine, and we'll find the coordinates of P. That last step is going to be fine because, well, at that point we're going to know the gradient of the line and an example of a point on the line. So that's sort of plane geometry in the plane, right, where you have a single point and a gradient. You can send a line through it. You know enough facts to find that line. And then finding the x-intercept is not that bad. So there's lots of separate things to do, but I don't think any of them are beyond you. So let's have a look then at my majestic version of this picture. There we go. Let's scroll down and look at what we're going to calculate. So, top tip for questions with circles and triangles and tangent things in, if you've got something that's tangent and you've got a circle, I would almost always draw in a line for the radius, because you know a fact, you know that that's at right angles, and sometimes that's helpful. So I might draw in these ones as well, because I know they're at right angles. This maybe helps me to discover a cute little square over there. I suppose these are 0, 1 and 1, 0 because of the square of side length 1. So if I needed to find this area, I'd be very happy because I'd find the area of the square, find the area of a quarter of the circle, and I would be done. Sadly, that is not the question. But I found a little square, so life could be worse. No, really wanted to erase that bit. Okay, I'll leave it. Fine. Keep your colouring in. Ooh, did I miss something? What did I do? I was drawing it and I couldn't see something. Good. How much reasoning are you supposed to do? So I think for this, you would explain what you're doing. I'm going to do it out loud. This question was set back in the days when the test was done on paper, so people could draw a diagram like this. You are not expected to draw diagrams for the long questions on MAT 2025 because you're typing answers using a keyboard. So I'm going to do this geometry question anyway. I think it's good for us, but we're not going to worry too much about how we would explain our reasoning in words. The people who did this question back in 2007 could explain by drawing pictures. Good, okay. I've got an angle of theta down here, which is not exactly making me nervous, but, well, I think I'd like to know what the gradient is to get from 1, 1. So I've noticed that the thing I'm trying to prove about Q is that it's 1 plus something, 1 plus something else. So I'm being asked to say something about the relative positions of these points. I think if I could get the angle theta in a good place, then everything would be fine, because I would be able to say something like, well, I know the length of this radius is 1. It's one of the reasons to draw in the radius. You often know how long the radius is. I have this right angle, right? I have a right angle, and I've got a theta down here. So, ooh, not quite, but could I do something like drawing in a line like this? So this is motivated by the fact that I want to find out some angles. I've got a right angle over here, and I know an angle down there, which is not quite enough, but this is going to be okay, because if I draw this vertical line in, then I could find this angle. I suppose it's 90 minus theta, if I draw this vertical line here, 90 minus theta, and then this thing in here is going to be theta as well. And now I'm in a good place. So if I was explaining this in words, I would say drop a perpendicular from Q to the x-axis, let's call that point H or something. Drop a perpendicular from Q down to the point H on the x-axis. The angle HQ, has that point got a name? That point's got a name. HQP is 90 minus theta, so the angle HQ, I'll give a name to the centre of the circle as well, O. HQO is theta, because the tangent is at right angles to the radius. There's a right angle on this side as well. And now I'm in really good shape because I have this triangle OQ, and I'll put in a bit of horizontal line as well. This is the sort of triangle that I want to draw if I'm thinking about coordinates relative to O, because in Cartesian coordinates I want to say it's across a bit and up a bit. You can draw loads of triangles, but across a bit and up a bit is a pretty powerful thing to be able to say. I've got theta here, I've got 1 here, so now I think it's pretty clear that this is sine theta and this is cos theta. I might end up giving this point a name as well. I call it A or something. I don't think we've got A yet. I'll drop a perpendicular from O to QH. And I might describe all of this in words, but I do like the phrase drop a perpendicular. I wonder if you've noticed. Set up some right angled triangles. I've got sine theta and cos theta, which is, I think, exactly what I want, isn't it? 1 plus sine theta to get across and 1 plus cos theta to get up. Yeah, people are having a good job of it in the test. How rigorous does your proof need to be? The bar is lower than you think. The general thing that you should be aiming for, somebody in chat asks how rigorous will my proof be, which the bar you're aiming for is correct. Often I think people worry too much about presentation when they haven't actually got, first thing you need is you need an idea about what you're doing, and the usual reason that people don't get marks on the long questions is not lack of rigor or lack of explanation, it's because they're just wrong. So you can beat that by having an idea and being correct. The idea, once you've had a correct idea, is to put enough words that the person marking it knows that you've had this correct idea that you've had. So there's some clarity there that could be helpful, so that your idea makes it into the box rather than staying in your head. But, using words to describe what this idea is. I always think I'm always encouraging everyone to use more words, so don't take it personally if I encourage you to use more words. Good, okay. I knew these angles were equal because we use it as a rule in physics. Anonymous in chat has learned that angle that I've got in pink on my picture as a physics fact. There you go. I started this live stream not knowing any physics that uses triangles, and now, an hour and a half in, an anonymous person, thank you very much, has given me a bit of physics with triangles in. There you go. And there's a question about partially correct answers. Let's assume it's the same anonymous person. So if you've had a bit of an idea and you've explained part of it, then you might get partial credit. Often these questions involve doing something and then doing something else, so you can give partial credit for getting halfway through. And sometimes people have had a pretty good idea, but they've made a mistake, so they get almost full marks. And then we can give full marks to people who have justified their answers and maybe got the right number as well. The dream. Okay. Ginger Biscuit on screen has got this idea that the gradient of PQ, which is something else we're asked for in the question, is -1 over the gradient of OQ, because they're at right angles. We're combining together facts here from the Trigonometry live stream with the Geometry live stream. So gradient of q is going to be cos over sine. Looking at this little triangle again, I like drawing a little triangle. Often if you've got a complicated picture and you think you've spotted something, to draw a separate version is often a good idea, because then you could reread this picture as telling you something about the gradient from O to Q, cos over sine. So the gradient of OQ, let's write that out, gradient of OQ is cos theta over sine theta. It rises by cos theta over a run of sine theta. So the gradient of PQ is, these things are at right angles, so their gradients multiply to give -1 minus sine theta over cos theta, which is negative tan theta. And chat would like to know, because we were talking about marking, do you get error carried forwards marks? Sometimes. Often it's the case that if you make an error, then you're just doing something totally different from then on. But occasionally, on particular past questions, we've done error carried forwards if somebody's made a particular sort of mistake. It's not just always free for all, that if you make a mistake, then hey, you can do whatever for the rest of the question. But occasionally the marking team have done error carried forwards in particular places. And Anna would like to know how many people sit the MAT. It's a couple of thousand people. Yeah, we've got quite a lot of applicants. You could use the large triangle to find the gradient, couldn't you? Well, do you know where any of the points are? There's a bit of a problem. No, you could, because you've got this theta down here. So you know that there's kind of a, we don't know this length for this long line PR, but we know that this is PR tan theta. So it's fallen by PR tan theta over a, no, hang on. Sine theta. I've jumped the gun by writing tan. Jumped to the answer. Yeah, I like this. Okay, you can use the big triangle to work out the gradient. If you see just an angle theta, you can just go for it. That's brilliant. Maybe I should have started there. Because if I'd known the gradient, if I'd known the gradient of the line by looking at theta, if I'd known it was minus tan theta, if I'd done that first, then I could have found the gradient of OQ, and I could have used that, a fact about the gradient to write down something about the rise over the run for that little triangle. There it is, this little triangle. Together with the fact that its hypotenuse is 1, that would have been enough, I think. That's pretty good. Okay. Okay. And then Ginger Biscuit in chat has got something complicated involving 1 over tan. So we'll get the area in a bit, I think. Good. Right. We're not actually asked to find the area, are we? We're asked something quite complicated. Have I found the coordinates of P? No, I've been lazy. I've not found the coordinates of P. Well, we know that this goes through... Oh, people don't like it when I write this down too fast. But we know the gradient of the line is this. We know that it goes through the point 1 plus sine theta, 1 plus cos theta. So the equation of the line must be something like this. So that it has gradient minus tan theta. And so that when x is 1 plus sine theta, you get 0 in the bracket plus 1 plus cos theta on the end. I know that people don't really like it when I write that. Shall I simplify it? I think people prefer it when I simplify. So plus tan theta, and then what is that? Plus sine theta tan theta. Is that a thing? Not really. What a mess. I sort of think I've got that wrong. It's so messy. I really dislike that. Yeah, I'm not happy. I think it is that though. That's just awful. Can I do anything involving these terms? Maybe I don't particularly want to. These add up to 1 over cos. Because this is sine squared over cos, and then I looked for a cos squared over cos, so this is between them a 1 over cos theta. Don't like it very much. So I've got 1 over cos, I've got a tan, and I've got a plus 1. Those things have the same flavour as each other, I guess. Right, okay, have a line, part 2, and then we need to move on, I think. We've got these areas. We're asked to explain why the areas A of theta and B of 90 minus theta are related. When I see 90 minus theta, I'm thinking other angle in the triangle. So let's get another copy of this picture just to wrap up. when I see 90 minus theta, the thing I'm thinking of is this triangle over here. And of course there's a relationship between A and B in that picture. A is the area next to theta, and B is the area opposite theta, and the opposite of the opposite is the adjacent, or something like that, right? B is the area opposite, so B of 90 minus theta would be the area opposite the 90 minus theta and corner, which is a different description with the same area as A of theta. So they've got this kind of symmetry property. And if you set theta to be 45 degrees, then you get the fact that A of 45 degrees is equal to B of 45 degrees. It's an isosceles triangle. Those two areas would be the same if we were talking about 45 degrees. These lengths would be the same size. Everything would be lovely. And I suppose all we would need would be the area of the triangle, the area of the circle, and I suppose we'd subtract this little corner, and then divide by 2 if we cared about those areas. In the 45 degree case where they're equal, everything's nice and symmetric in the 45 degree case. And then the final case I want to put on the screen is the 60 degree case, where we know quite a lot of stuff. In the 60 degree case, just looking at A of theta, so let's modify this picture a little bit, don't care about that bit anymore. In the 60 degree case, where we want this area in here, the way I would go about this, I think, find this area into the corner as well. To find this area, well, that looks a lot like sort of a larger shape minus. I can see this bit of a circle that I don't want, so that's making me think what would happen if I put that in as well. It looks like 120 degrees. Is it actually 120 degrees? Quadrilateral, it's got some right angles, 90, 90, 60. Quadrilaterals always add up to 360 degrees, so I suppose that really is 120 degrees. So I've got 1/3 of a circle. Oh, slightly quadrilateral fun. 1/3 of a circle, and I've got some quadrilateral shape which has right angles in it, so I kind of split it in 2 to make triangles, right angle triangles. I know how big right angle triangles are, so I think this looks good. This is now 2 30 degree angles with one over here. So this is 30 degrees is the top of an equilateral triangle, right? Split in 2, so this is √3/2. And then the area is √3/4, but there are 2 of them, so √3/2. I think I've dropped a factor somewhere. Yeah, I think I've dropped a factor of 2 somewhere, but I'll live with it. Just √3, isn't it? Just √3. This is 2 down this side. There's the factor of 2. The only factor of 2 on the screen. √3 down here. 60 degree case is very nice. No, sin x times tan is not cos. It's the other way up. The other one. The other one. Good. Okay, we're not asked to calculate A of theta in general, but I reckon you could use something like this to do that. Split it in 2. You can always work out this angle in the circle based on the other angle, and then you'll have a pair of triangles. I've sped through that, really sorry. I talked a bit while I was doing it, so hopefully if you are having trouble splitting down the area, the common theme, I think, is sectors of circles. So if you can see a way to add a bit of a circle back in, then that's good. Or subtract something from the area of a sector. We've seen that before, haven't we? We had a circle where we might chop a bit off, and then you've got a sector of a circle minus perhaps a sector of a circle minus a triangle. This one's kind of the other way around. It's triangles minus a bit of circle. I think there's a visualization thing. I wouldn't have seen that if I'd been still looking at this diagram, right? Because I would have drawn in, oh gosh, I would try to shade this bit and then I'd be in a mess because I've got this bit down here, so I would probably get distracted by trying to find this area or something horrible. And oh gosh, straight line circle, this is the hard thing where I would then try and find this angle of the eye. It would be awful. Drawing a new clean picture was really important to me to actually get through that. Yes, is A 45 square root 2 plus 1 minus 3/8 pi? I think it might be. Let's have another look. Yes, it is. Well done. Good. Which sounds something like area of a triangle minus a circle minus a little bit divided by 2. 45-degree case. 45-degree case, just to illustrate the thing that we were talking about before. 45-degree case looks like this. Oh, I've got squares, I could use those. Whoops, I should have thought that before. 45-degree case, we were asked for one of these areas over here. My strategy for this, I suppose, would be things I don't want are square in this corner, 3/4 of a circle, and then divide by 2, because I have A and B. I only want one of them. So I'll need to know how big the triangle is overall, and then I'm going to subtract a little square, subtract 3/4 of a circle, and divide by 2 for the 45-degree case. You can use that to derive sine of 22.5 degrees, can you? Ooh, sounds fun. Do I know sine of 22.5 degrees? I'm not sure I do. Fun. I'd use double angle formula, and that's not on MAT, so we're going to move on. Right. Okay, I like this question quite a lot. It's got a kind of symmetry idea, it's got all of this coordinate geometry stuff where there's different approaches you can use. We went for earlier this kind of draw a small triangle. I love drawing little bits of picture. It's quite time consuming to put that into the solutions, so it's something I feel like I do better on the live stream than I do in the work solutions on the Mat Live page. You've got to be not scared of drawing in some extra lines. I've drawn in, how many? I don't like the green one, but I've drawn in 3 radii, and I've drawn in this pink line here. You need a reason for drawing in lines, don't just connect points at random. My recommendation is radius to a point of tangency is usually good because you know a fact, you know a square root, you know a right angle fact. So radius to a point of tangency is usually good. Tends to break down your picture into sectors of circles. If you've got a few radiuses in, you know about areas of those things. And then the pink line was a bit more dubious. Not sure if you necessarily need that one. My defense for that one was I could do some angle chasing. If I felt like I needed more angles, I wanted something relative to a kind of vertical line, sort of plumb lines. But I like dropping perpendiculars. I think you can do the question without drawing in that pink line if you prefer. Okay, should we balance the circle on a parabola? Seems like a fun thing to do. There's a diagram. This question is from 2012. It's been modified in the sense that it's now written in degrees, which, if I'm honest, has kind of ruined part of the question down here. That's just so ugly using degrees. Oh well. That's also using inverse cosine, which has reminder text in square brackets. Okay. Let's look at the idea for this question. So there's a parabola, y equals x squared, and a circle which is just resting at a tangential. Now, reminder, that means that they have a shared tangent at that point. 2 curves can be tangential. I guess the first time you meet the concept of a tangent, it's a straight line that's tangent to a curve. And you're told, the important thing is that they have the same gradient at that point, which you could say they have the same tangent. One of them is the straight line. Curves can be tangential to each other as well, though. The rule is the same, that they have the same gradient at that point. Or, if you prefer, draw in a straight line and point at the straight line and say they both have the gradient of that line. So I'm imagining kind of shared tangent at point B. This is going to matter because I think we're going to be asked to find out what's going on, and a shared tangent is an equation. I like equations because, well, lots of questions turn into equations, and then we solve the equations, and then we're done. Right, okay. Yeah, okay. Sorry, think about tan 25 again, 22.5 degrees again. We get to qxy, use the distance formula. Ooh, distance formula. Yeah, okay, so speaking of equations, there's a suggestion in chat that with the previous one, a definition of q is that it's a point on that line such that the distance to the centre of the circle is exactly 1. If you write down that as an equation, then you get something which you can solve for the coordinates of Q. I like that as well. You need to find the line first, which we've considered a little bit because tan theta. Work out the gradient of the line first. Okay, so looking at this diagram, the way I would try and work out what's going on, I haven't looked at the question yet, but the way I would try and work out what's going on is, I know everything about the parabola, so I know its gradient, so that's fine. Is it the case that I could necessarily work out the radius of the circle? I think not yet. I've been told the centre of the circle. That's interesting. So if I'm told the radius of the circle, I'm being told, I suppose, here's a beach ball, or is it a ping pong ball? I'm going to drop it in. It's not obvious to me that if you drop a ping pong ball in, then it will get stuck like this. It might go and sit at the bottom if you fix the radius of the circle. If you drop a beach ball in, then I reckon it can get stuck like that one in the picture. But if you drop a very small ping pong ball in, then won't it just sort of sit at the bottom of the valley? So there's something going on there. But they haven't told me the radius, they've actually told me the centre. So maybe my mental image is something like, I don't know the radius of the circle. I've just realised I haven't been told the radius of the circle. So I'm going to imagine, is it a very small circle? Well, no, because a very small circle would just be a little circle around the coordinate 0,2. I've been told its centre is at 0,2 in the middle of that picture. Is it very small? No. Is it huge? No, because then the circle would be so far away that it would just cross the parabola and then go miles away. There's somewhere in between. It doesn't seem that bad that we could, increase the value of r until we get just tangent. You could probably do something with equations here to say, I don't know r, but there's the kind of only one solution for points that are on the parabola and the circle. I like that, I think. There's some stuff with tangents and gradients, but maybe what I like is thinking about radius, if I was going to approach this question. Right, time to read the question, I think. Yeah, so we might use the discriminant, or we might use some facts about gradient. For the gradient of the circle, you probably want to use some trigonometry. It's the Trigonometry live stream, so that's how I think about that. Okay, everyone's got that picture in mind, I hope, with the circle resting on a parabola. That's what we're calling it. Okay, time to read the question. Have I gone too far? No, I'm good. In the question, disappointingly, we're told to use gradients. We're told to find the gradient of the line joining the centre to this point. So I think we're being led in the direction of thinking about gradients. I want to think about discriminants separately, I think. So part I here, we don't know the xy is the point on a parabola. Oh, excuse me, xy is a point on the parabola, so that's x is not 0. The gradient of the line joining this point, I've drawn the wrong picture. I've drawn a point on the circle. Let's see if I can convert that picture. Perfect. So the gradient of this line to get to x, y is equal to x squared? Yeah, y is equal to x squared. So the gradient is the change in x values, change in y values divided by the change in x values. Oh, it's getting late, isn't it? There we go. So x squared minus 2 divided by x. Oh, brilliant. Okay. And then I think what we're being led to is to think about gradients. Yes, look, we're going to find the coordinates of B as the name of one of the points of tangency. So we could play along with that. It says, with the help of the result from part I or otherwise. So, I'm being led in a direction to think, okay, that's the gradient. I would like that to be at right angles to, I'd like that line to be at right angles to the tangent to the curve, because I want it to be a radius tangent sort of situation. Could go down that route, but I want to do it the other way, I think. So psych, let's do this thing instead, where we don't know r at the moment. We're going to work out r probably because I think we're going to solve everything to find the point b. And we also know that y equals x squared. For talking about the point b, it's on both of these. So what do I want to do? I've just noticed that if I plug this in, I'll get a very horrible expression. Am I going to enjoy that? I'm not sure I'm going to enjoy that. Maybe this is a mess. Maybe not. Maybe this is fine. I was hoping for a quadratic, of course, to get some repeated roots. It's not looking good because when I plug this in, I'm going to get x to the 4. For tangency, we want x minus 2 squared plus x to the 4 equals r squared to have a single positive root. Single positive root. Don't love it. Anything clever we can do? Maybe not. Y minus 2 squared. Excuse me. Y minus 2 squared. Thank you, chat. Is that good or bad? Oh, goodness me. I've gone off script. Is this good? Not sure this is good. I sort of think this is bad. Oh, that's very good though, isn't it? That's great, because that's a hidden quadratic sort of situation. This expands to give no x term. The one I was considering for a moment there was unpleasant. But this is all right. This is a quadratic in x squared. So we'll always get symmetry, plus or minus solutions, but we could hope for a single positive root. If, for example, so is there a single positive number that does this? I might just set the discriminant equal to, I'll just set the discriminant equal to 0 and see what happens. If you do that, you get b squared minus 4ac equals 0. Is this what I want? Don't know if this is what I want. What I really want. It's not bad. I feel like I've screwed up some numbers. Yeah, I have screwed up some numbers. Yeah, 3 in here. Thank you. Thanks everyone. Chat's being very helpful. B squared minus 4ac. There we go. Thank you, chat. As is sometimes the way, I knew I'd made some sort of mistake. Okay, 16 and 9, 7. So r is. Well, I've got my radius now. Is that good? Oh, I think that's very good actually. I've got the radius of my circle to get a repeated root. If I do that, then is there definitely a positive root? Yeah, probably. Yeah, this thing will be negative if r squared is 7. Nervous. Yeah, this is fine. This is fine. The sum of the roots is positive, so there is a positive root. Yeah, good. Okay. If I swap the centers, I've made a couple of mistakes. Oh, sub in u equals x squared for that particular solution. Yeah, let's go. We were trying to solve the thing, weren't we? We wanted the value of x. Let's go. Chat's leading the way. It might look like I'm doing things, but I'm just a puppet for chat. Here we are. Oh, I could have completed the square. That would have been fun. Completing the square, I would like 4 minus r squared to be 9 over 4, or something like that, maybe minus 9 over 4, in order to get this thing, which then has a repeated root. exactly when we get this correct value, because in this case 4 minus r squared is exactly 9 over 4, so this is perfectly this. So u really is 3 over 2. It does have a positive root, so x is square root of 3 over 2. Is that the thing in the question? That is the thing in the question. That's a very nice method at the end. I like that. It gets us to practice something we did in the algebra live stream ages ago, involving a polynomial with an x to the 4 term and an x squared term. It's just off the top of the screen. X to the 4 term, x squared term, and a constant term. And I got several of the numbers wrong, and I missed another minus sign. I even shifted x and y the wrong way around, having a bit of a problem. But at the end of the day, we get this radius down here, which I can see all these 7s and 4s and pi's in this weird expression. 7 pi over 4. That's a circle fact, isn't it? That's pi r squared if ever I've seen it. We get this root 3 over 2 fact. Good. Okay. Why do I set the discriminant equal to 0? Well, after I've made this substitution, I know that that's including positive and negative values of x as the same value of u. So there's this kind of strange fact that although you're right that I'll get positive and negative values of x, two solutions, those are both the same value of u. But I know that, I'm anticipating it. The thing I'm worried about is whether or not you get two values of u. Let's do a Desmos quickly. Great job, James, and mostly chat. That seems fair, I think. Quick Desmos, just for that expression, x to the 4 minus 3x squared plus 4 minus, and then I'm going to use the letter a because Desmos has special feelings about the value of r. So you see, for different values of a, you might get two positive solutions like that, or just one positive solution. Or this kind of special case where it's perfectly tangent at root 7 over 2, where it's perfectly tangent at root 3 over 2, the value of x. The substitution that we've done is to take that expression and to rewrite it as, to instead consider this quadratic, which looks wrong. Oh, it's a rescaled. There's a rescaling going on, so this is actually at 1.5 now. And I want you to notice that the red curve has this lovely symmetry, the green curve gets rid of that, and a single solution for the green curve, like this, gives us two solutions for the red curve. So we get two values to do with the square roots of this number. The rule is that things on the red curve, the x value is the square root. And then of course there's a negative square root as well. So you get this red curve having symmetry, and there's some square roots going on. Oh, this is a good demonstration as well that for the green curve, one of the roots is larger than 1, so the square root is smaller. And for the green curve, one of the roots is less than 1, so the square root is larger. The red curve is showing all these roots, and the red curve are square roots of the roots of the green curve. Good. Chat is voting a little bit about GeoGebra, which I've never learned to use. The thing I like about Desmos is that I could make this very, very, very quickly, which is good, of course. We've gone slightly long on the stream, which actually means that okay, so, brilliant. Let's just put chat on for a bit. Slightly long on the stream. So what I could do is I could look at part 3 if I'm feeling very brave. I mean, we could talk about part 3. Ginger Biscuit has noticed that the coefficients spell 34, which is excellent fact. Well done. Good. You know, if you do 44 more chat messages, then you'll hit 340 total. Just saying. I can play this too. What are the votes like on these Desmos GeoGebra thing? No, the Desmos one's got a thumbs up. I'll take that. I'll carry on using Desmos, thank you. What's the average of 67 and 69? Let me just work that out. I think it might be 68 divided by, wait, 4? Okay, so divide by 4. It's not quite the average of 67 and 69. They want me to then divide that by another factor of 2. Right, where it says goodbye to all the biscuit themed people in chat. As I say, I don't pretend to know what's going on at any given point. Right, okay. Let's carry on with the question. I think that's a wise choice. So the question has all of these factors of inverse cosine of 1 over root 7, this arc cos thing, and 180 degrees. So I'd like to know what's going on there. I think that's my ambition for the rest of this. Parts 4 and 5, by the way, I think are definitely easier if you do this algebraically, so we might have jumped the gun on algebra. Look, in part 5, let r be the radius, expressed as a function of r, distinguish between the cases in which the circle is. How high up do you put the circle? That seems like algebra, where there's also a parameter a inside the equations, so our discriminant might involve the value of a. And we might flip between the cases where, if you work out the degree 4 polynomial, x to the 4 plus some multiple of x squared plus a constant, there are different cases, the ones that look like w, and there's ones where you get the different numbers in there, it just looks like an x to the 4, but more so. Those different cases give you different numbers of roots, and they give you different positions for the roots as well. So maybe we'll find different cases like that. Especially if you want a repeated root. Totally different if you have this W shape or not. If you haven't messed around with polynomials, then I encourage you to mess around with polynomials, either on a graphing calculator or Desmos or GeoGebra or something. Once you get to degree 4, you can do lots of different things, which, you know, if you're supposed to be good at doing things with polynomials, so having a look at some polynomials, that's probably a good idea. Desmos is free. You've seen how easy it is to type in polynomials or something to see what happens. Is it obvious what I'm doing in Desmos? People know that you can do powers using the thing above 6 on a keyboard. It's this kind of carrot-shaped thing that I use for signing comments, but you can also use for powers in Desmos. Back. It's not bad. Right. Okay, I'm going to aim for this fact involving 180 degree facts, and I need an understanding of what it's describing. So it's a sector of the circle enclosed by the radius to A, the minor arc AB. Well, I've drawn a parabola, but hang on a second. I just want a circle, don't I? At this point of the question, we know where everything is. Great effort, we've worked out where the points A and B are. Well, I guess we worked out B, but A is the mirror image. Have another go at that. So I'm asked for, it says minor arc, but it means this sector down, this stuff down here, doesn't it? And we know where everything is. So this is a slightly funny question in a way, that the parabola is no longer relevant, I think. It served its purpose. And now we just have this question where we know 3 points. We know 3 points. We know the radius of the circle. Or do we know the radius of the circle? Well, I do, because I did some maths just now. If I was paying attention, I'd know that it's root 7 over 2. And we just need to work out the area of this sector. So it's pi times this thing squared times, well, we've got to work out that angle. But working out that angle is not too bad, is it? We know everything about this triangle. We know where all corners are. So I suppose I just need to draw this out. I want this angle. I know these things are both r. I'll go back to writing r because I didn't enjoy writing root 7 over 2, and I'm worried that I've got the factors of 2 wrong, and I only want to fix one of them. And this width out here is twice root 3 over 2, which is a bit of a mess, but I've seen worse. Do I want to rewrite that as root 6? Maybe I do. Surds. Okay, I would like to find cosine of this angle, because the question is all about inverse cosine. So I suppose I need to write down the cosine rule. that wasn't too bad. And then I'll need to, what's the quickest way to do this? Probably divide by 2r squared first. 2r squared is, r squared is 7 over 4, so 2r squared is 7 over 2. So we'll divide by that, we've got 12 over 7. It's 1 minus cos alpha, and now I feel like I've gone wrong. No, I haven't. Cos alpha is minus 5 over 7. So I just want that. Oh, minus 5 over 7 in the question. So this cos inverse minus 5 over 7 is this thing. Now why is there 180 degrees in there? And why is there a 7 pi over 8? What's going on there? Oh, it's because the area of a sector is something like pi r squared. Pi r squared, that gives us this much for the pi r squared, pi times 7 over 4. But then you have to do this horrible calculation of alpha divided by 360 degrees. Which is why it says 8 down here on the right and 180 degrees over there. Ah, I see. Okay. Yeah, so I'm going to end up with this expression. So I've got this alpha, I've got the cosine minus 5 over 7. The other one comes if you drop a perpendicular down the middle. I do like dropping a perpendicular. And you think about just the triangle on one side. You find something that involves a smaller triangle, sure. But you know quite a lot about that triangle. You know its height, its width, you know all the side lengths. You can find the angles in that triangle if you want to. Maybe that's easier because you know the height is. You've got to do some differences. Height is 1/2. That's maybe nicer. This y coordinate is 2. This y coordinate is 3 over 2. So the height of this triangle, if you care, is 1/2. And then you do, because you just get this nice 1 over root 7 factor from cosine of this kind of half angle in here, which you might then want to split the sector in half and double it at the end. Good. Okay. Somebody tells me there's smart draw in Miro, and I refuse, I think. Are we doing? Yeah, okay. Yeah, let's find some distances. I think we're good. Okay. Oh, I've just realised the chat comment that is about Wikipedia. So someone's registered the username. It says the first number without a Wikipedia page dash 281, which I haven't read out yet because I think it's false. I think it's not 281, but I've realised that that dash is actually a minus sign. They're encouraging me to do some subtraction because the smallest number without a Wikipedia page is 315, which is the number of chat comments right now. Not good enough for a Wikipedia page, but chat's at 315 comments. I subtract 281 and then you get a familiar number. Well done, everyone. Good. I should say to Georgina, if you're watching, that I said you could stop at 7, so I should probably let you stop. I think we're wrapping up. We've got a cosine rule final at the end to get this fact. There are 2 versions of this in the question. Let me quickly check. Is that part of the modification? Back in 2012, did they have both versions in the question? Let's have a quick look. Is that part of the modification with MAT Livestream? Question 4, back in 2012? I can't remember. Let's load up the old one. No, only one version. You were supposed to split it in 2 back in 2012. If you did it the other way, then you'd get a different expression, and you might not know. In 2012, this question just had one expression, much tidier because it's using radians, and because they've only got the one version. That's a bit of a mess, though, isn't it? Right. Okay. Right. What are we doing? I think we've settled about decimals. Didn't get what we put discriminant equals 0. Oh, back here, I was hoping that there'd only be one solution for u. I was a bit worried about whether it was a positive number or not at the time, so I didn't talk very clearly. But I only wanted one solution for u so that there would only be 2 points where the circle met the parabola, rather than, well, the normal answer would be 4 points, I suppose, for the circle crossing the parabola twice on both sides. 4 solutions for x means 2 solutions for u. And so I wanted to set the discriminant equal to 0 to make sure I would only get one solution for u, just to see what would happen. That would correspond to two values of x rather than 4, 2 on each side, crossing on both sides. That's kind of normal situation. If you imagine inflating the circle larger and larger, then you get no solutions for a while, and then generically you get about 4 where it's crossing the parabola on both sides, but this perfect moment in between where it's just tangent, you get one solution on each side. Good. Okay. I think that'll do for a live stream, more or less. We've done the last part of this question. We haven't done the last two parts of this question. The question does keep going from there for some reason. Oh god, I've got 5 minutes. 5 minutes to finish the question. I've got to finish the question. So I think we're being asked to repeat stuff based on, we've done quite a lot of work already. So the circle is now at 0a. And we're asked for the range of values of a for which the circle and parabola touch at 2 distinct points. So this really feels like I'm supposed to what? Oh, he's resting on the parabola. The question is kind of, is that even possible? It looks possible. It looks impossible in the picture I've drawn, but it was possible a moment ago. Something like this. So the problem is apparently if the circle is too low, then you can't make this happen. Let's try and solve and see what happens. So we're trying to solve, we'll do it algebraically again. At the intersection points, we have this. I'm going to get it correct this time by concentrating. We don't know the radius r. We're interested in finding a value of r such that we want one positive solution for x. It's not obvious that that's going to happen at all, so let's go looking for it. Ooh, squared outside the bracket, whoops. Don't write over the top of it, try and fix it properly. So if I plug in y equals x squared to see what happens, then I get this quadratic expression. I'm going to get this one right as well this time, there we go. And then the question is, do we get, so this is an expression for x squared squared, I suppose, and then x squared. We're being asked for different values of a, what's going on? You can change r squared, of course, and then maybe you get solutions or not. But the question is, can you choose r to just get one solution for x that's positive? You always get positive and negative pairs. I'm going to complete the square, I think. Oh, it's a square inside a square. We had one of those before and it was confusing, so best of luck everyone, including me. What do we have? A squared minus r squared, and then I need to subtract 1 minus 2a squared over 4 if I'm completing the square. So then I suppose part of my concern is whether this thing on the end is positive or negative. Or not including the r squared somehow. Because if this thing a squared minus that stuff is negative, then whatever value of r squared I take, it just gets more negative. Is that good? Maybe that's good. Maybe that's good. Yeah, okay. So I definitely want this to be quadratic science. Quadratic science. I definitely want Okay, if this thing on the end is positive for all values of r, then we're just in trouble. That doesn't happen, but if it did, it would be a problem because we couldn't make 0 out of these two positive things. So it's always the case that you could get some solutions if you make r large enough. Those solutions, well, there's going to be two of them from the kind of plus or minus thing that's going on here. Oh, the a squared is going to cancel. There's a 4a squared divided by 4 here. That's going to cancel with this a squared. This is not as bad as it looks. Possibly I should multiply it out and get something involving a and something involving 1/4, which I believe is the answer. So maybe I should go and look at that. Yeah, let's just simplify this a little bit. So this a squared cancels with the a squared over here. It's minus 4a, so I'm going to put plus a. We're going long today, but that's okay. So all of this stuff on the end, same square bracket stuff. Forgive me for not writing out the square bracket again. All of this stuff on the end, there's a 1/4 with a minus sign. There's minus 4a over 4 with another minus sign, so a, and there's a minus r squared. So if a is greater than 1/4, then you can choose r squared so that this thing is 0. And then you get, well, exactly this quadratic, you get plus or minus x, and that's all fine. So if a is greater than 1/4, choose r squared equals this positive number, a minus 1/4, and you get two solutions. Get x is plus or minus root 1 minus 2a over 2. Oh, quick check, is that positive? That doesn't look very positive, does it? Minus sign, 2a minus 1. Oh, is that allowed? 2a minus 1. Suspicious that I actually wanted a 4 in there as well. That's not good, is it? Because then if a is only a third, this is negative, so this is terrible. We don't get any solutions. That's interesting. So then we fail inside this bracket to get any solution. Yeah, Vikram in chat. Thank you for joining chat. Brief comment on how time is allocated during the math. You can allocate your time however you like. You get 2.5 hours. You don't get moved on at any point. So if you want to do 2.5 hours on the first multiple choice question, well, that's allowed. You're encouraged to look at all of the questions, including those long questions at the end. There's a navigator button, so you can jump to them whenever you like. You can go back. You can return to questions as often as you like. You can jump around as much as you like. There's a review screen to jump back to questions that you haven't answered or haven't seen, and you have 2.5 hours. That's timing on the map. It's not allocated for you. Yeah, I think I'm worried that if a is between 1/4 and 1/2, then I can choose r squared to give me 0 over here, but then I don't actually get any solutions because this thing, it was positive inside here. I'm not sure that's a real case though. I think I've just confused myself. Yeah, okay. So this thing on the end, this constant on the end, if it's positive, nothing doing. If it's negative, then you get two sorts of solutions. One's where x squared plus this stuff is plus or minus that. And then I'm interested in whether or not they work. That's pretty subtle. So maybe I want to go back to thinking about the discriminant and thinking about whether or not you get positive solutions. And sort of this two-step process because I've got a quadratic inside a quadratic. So maybe I want to go back up here and think about the discriminant. Minus 2a squared minus 4a squared minus r squared. Oh, this looks nice. This is 0 if, and the 4a squareds cancel. 1 minus 4a plus 4r squared. Okay, so that's the same expression And maybe this is my justification to say I want to take r squared to be that value. This is a different reason to choose r squared is a minus a quarter, which only works if a is greater than a quarter. Yeah. So I'd treat a is unknown, r is unknown, x is kind of unknown as well. It's solutions for x that we're particularly interested in, so I'm willing to treat a and r as sort of fixed numbers that we just don't know, whereas x is the thing where we're trying to find solutions. So I would look at the discriminant of this in terms of a quadratic in x squared, I think. I'm very interested in whether or not we get positive solutions, and I think I've confused myself with the nested quadratics. I am running out of time. Chat is running out of time as well. I don't even know which part of the question I'm doing. Express a as a function of r. I've sort of already done that bit. A is r squared plus a quarter, right? Have I overthought this? I think I've now overthought this. The solution in the worked example, the worked solution in the MAT Livestream pages disappointingly uses the gradient method, which we've been ignoring. Maybe that would have been better at this stage. And the crucial thing is a versus 1/2. Interesting. So I don't know what's happening between a quarter and 1/2 at the moment. I need to go back and look at the gradient. Right, okay, different method. Go and think about the gradient. But with the number a instead of 2. Don't like that. I feel like I should be able to defeat this. So at this stage it's clear that I need a to be bigger than 1/4, but then actually even if a is bigger than 1/4, you can now choose your value of r squared, hooray, to get 0. But then maybe if this thing, if a is less than 1/2, okay, so I think it had all the right ideas, just lacked the confidence to say all of them in one big sentence, which is that you need a to be greater than 1/4 so that you can choose a value of r squared such that this thing is 0. And then with that, you've still got to pass another test if you're just looking for one positive value of x, which is that you need this number in here to be negative, which happens if a is larger than 1/2. And it's those things together which mean that you end up with exactly a situation where you have x squared is equal to some positive number once you've moved it on the right hand side. Otherwise you have either negative number. I mean, should we write it out? This is the thing we're trying to grapple with by doing this algebraically. That what we have is, if you put square roots on, just go for it, right? We have x is equal to big plus or minus sign. That's our kind of first plus or minus sign. Let's forget about that one for a second. But like the positive solution is, if it exists, 2a minus 1/2 plus or minus the square root of r squared minus a plus a quarter. Then move that over, square root it, and then move that over. I want a positive number, so it's sort of checking that, well, checking this bit exists, this square root bit exists, and then also checking, a single positive number means something like, I then also need to make sure that I have a positive thing over here. There's another plus or minus sign out the front of all of this, and a square root actually, now that I think about it. Yes, I haven't quite inverted, I've got x squared is equal to this. I suppose you could you set this to be very large? If this is very large, and then this, could it be the case that this is so large that one of these roots is negative? I think the answer is no, but it's not obvious. Okay, right, gonna call it there, I think, at 7:30. We've got bonus half an hour. And we reached exactly, they've even stopped messaging, well done chat. They reached exactly 340 chat messages, which is of course what they wanted to do. I'm going to have to explain to Georgina after the show what that was all about. Thank you everyone. Have a nice evening. Have a nice, okay, let's put the celebration on chat. Have a nice evening. Have a nice weekend. Enjoy the rest of your maths and the rest of your summer holidays. We're back next week for sequences and series. It's going to be a good one. at least some of us, I think, are going to learn new facts about sequences and series before you've learned them in school or equivalent. But for everyone, I think we're wrapping up the stream there. So thank you very much for joining in. Have a nice week. We'll see you in 165 hours for another episode of the Oxford MAT Livestream. Take care, everyone. Bye.